Welcome to today's Trane Engineers Newsletter Live program. I'm Jeanne Harshaw, and today our program will focus on modular chiller plant design. As modular chillers grow in popularity and acceptance, understanding the nuances of these products and how to apply them in a system is critical. A modular chiller is designed to make chilled water or hot water just like any other chiller. But there are some key design features and aspects of modular chillers making their application different from packaged chillers. This E&L explores the key features of modular chillers and their applications. Today, we're going to start the program by giving a brief introduction to modular chillers, then cover equipment considerations, system considerations, and finally, applications where modular chillers are often used. To cover this topic today, we have Trane application engineers Dan Gentry and Sarah Hilden, and a guest presenter from our chiller product support team, Esti Tierney. Sarah is going to get us started with an overview.
Before we jump into the fun stuff, let's cover a few key terms. The first term is module. A module is a refrigeration unit containing all the components needed to produce conditioned fluid, as one would expect in a chiller, along with electrical connections and controls. Optional accessory modules can be applied to systems like pumps, expansion tanks, buffer tanks, glycol feeders, and the like. The next term is modular chiller. A modular chiller consists of one or more modules acting as a single entity. Like a packaged chiller, a modular chiller has single-point water connections, may include single-point power, and a single building automation system communication connection. Each module has a control unit, but the chiller is controlled by one controller, designated as the primary controller, staging circuits on and off to maintain leaving fluid temperature. Single-point power is available, making the individual chiller modules working together look like a single chiller from the electrical side when applied. Finally, a modular multi-pipe unit is a cooling and/or heating unit, typically consisting of two or more refrigeration modules and accessory modules assembled together to create a multi-pipe bank. Modular chillers are characterized by their field-assembled nature. Individual modules are shipped separately to the job site and assembled with integral interconnecting valves, piping, and controls. A single-point power connection to the chiller completes the set. Let's take a quick peek inside a modular chiller to see what's in there. A water-cooled module, shown on the left, has 4 pipes, one set each into and out of the evaporator and condenser. The air-cooled example on the right has just the 2 pipes in and out of the evaporator. The header pipes are connected between modules of a modular chiller. Both examples include dual scroll compressors on dedicated refrigeration circuits and raised plate heat exchangers between water and refrigerant. It's worth noting that shell and tube heat exchangers and different compressor technologies are also used in modular chillers. Either manual or motorized isolation valves may be included as standard or as an option. This varies by manufacturer. Ensure isolation valves are available per module for service, allowing the chiller to continue to condition fluid. Motorized valves are necessary for variable primary flow systems. More to come on that later. Main point here, each module is itself a chiller. Now, because flow is provided to modules piped in parallel, we need to consider how flow differs from what we're used to in a packaged chiller where the fluid stream has only one heat exchanger in play. Let's look at this even more generically. Each module is hydraulically in parallel with the rest. Every module has at least one refrigeration circuit, usually 2. Here the cylinders represent compressors. Each module contains a dual-circuited heat exchanger. The chiller itself has just one set of water connections, inlet and outlet to the evaporator and condenser if water-cooled. Here only the evaporator connections are shown. Let's say this represents an air-cooled modular chiller made up of 4 modules. You'll see a lot more of this diagram today, so I wanted to tee it up for clarity. At design, the system flow is 400 GPM. Each module presents the same pressure drop to the header. Therefore, each module sees 100 GPM fluid flow. Now we assume the system flow has dropped to 300 GPM. Each module now receives only 83 GPM. The takeaway is module flow is always proportional to flow through the chiller. Now you know what a module is and how flow is distributed amongst them. I'll turn it over to Esti to continue pulling this thread with equipment considerations.
Thank you, Sarah. Now that we've learned what a modular chiller is, we're going to move on to designing our modular chiller. One of the advantages of a modular chiller is the flexibility to use different module types and sizes, but that same flexibility can present a challenge in choosing the right configuration for your application. We will consider 3 main points to help determine chiller design. Let's cover the number of modules used in a design, compressor staging and operation, and lastly, delta T and temperature control. We will start with sizing our modular chiller. Simply said, the more modules in your chiller, the larger the footprint you will have. For example, you could use a single 80-ton module to meet an 80-ton load, but you could also use multiple smaller modules for added redundancy. Since modules of the same capacity are essentially the same physical size, an 80-ton chiller that is made up of 4 20-ton modules would be 4 times the footprint of one 80-ton module, even though the overall nominal tonnage is the same. Making sure you have the appropriate amount of space allotted in the mechanical room is just the first step. Footprint needs to be considered, but should never be the only information influencing the number of modules. This brings us to our second point. One of the main drivers for using a modular design is the desire for redundancy in a chiller system. A typical module has 2 refrigerant circuits, giving very little redundancy in a single module design. The more modules you have, the more redundancy in your chiller. Critical cooling applications will typically be designed with an extra module to meet N+1 requirements. Lastly, and arguably the most important, the steps of control needed in a modular chiller design should drive the number of modules used. When we say steps of control, we are really talking about the total number of compressors. Since most modules utilize on-off scroll compressors, a single module has only 2 steps of control, 1 compressor running and 2 compressors running. As you can imagine, this doesn't give very tight temperature control and may signal you need to use more modules. Keep this in mind as we move through the compressor staging section. In summary, deciding how many modules to use in your modular design should be a consideration of footprint, needed redundancy, and the steps of control required for your system design. Let's look at compressor staging on the modular level. 2 compressors are shown in this module, each on its own refrigeration circuit. We have a common dual-circuited braze plate evaporator. This means we have 1 water circuit and 2 refrigeration circuits in this module. We will assume a 16-degree delta T with a 60-44 chilled water design. What this means is when I have 2 on-off compressors, each of the compressors is doing an 8-degree delta T. Only when both compressors are running are we doing the full 16-degree delta T. When a system does not require full capacity, the return temperature back to the chiller may be less than the design entering temperature of 60 degrees. As entering temperatures to a modular chiller decrease, the primary controller will stage off compressors to achieve part load operation. This picture demonstrates part load operation with 58 degrees coming back to the chiller and only 1 compressor running instead of 2. Note this does not happen instantaneously. There is a delay, typically several minutes, between each compressor start and stop, allowing the modular chiller time to adjust to a dynamic system. 1 compressor running does half the design delta T, 8 degrees in this case. With only 1 compressor running, you can see how we vary quite a bit from the leaving chilled water set point, making only 50-degree water. If the entering water temperature continued to decrease due to low loads, you can see how 1 compressor would cycle on and off to meet the decreased load the best it could, with temperature fluctuation. The real way a modular chiller bank meets varying system loads is by utilizing the multiple modules with multiple steps of control to achieve a mixed water temperature output. When we look at 3 modules operating in parallel, we can see the mixing effect. This 3-module chiller has the same part load scenario we just looked at with 58-degree entering water. Here, the lead controller of the chiller bank again knows that it is a part load situation, but has more steps of control with which to meet the system demand. The first 2 modules do the full 16-degree delta T, and only the last module has 1 compressor running doing an 8-degree delta T. So 2/3 of your leaving chilled water is 42 degrees, and 1/3 of the water is 50 degrees, making the overall mixed leaving chilled water temperature of the 3-module chiller bank 44.7 degrees, and much closer to the overall chiller set point of 44. Remember when applying your modular chiller that the more modules you have, the more steps of control exist to match the design set point and the tighter overall temperature control you have as a chiller bank.
Esti, electrification is a hot topic today. Modular chillers are used frequently for heating applications due to their ability to function at high lift. What detail do we have on controlling to a leaving condenser water set point instead of the leaving chilled water temperature?
Dan, I like your subtle plug for electrification, so this example is for you. Most modular chillers built for heating have the option to control to the leaving condenser water temperature. What this means is that the modular chiller heater will stage compressors on and off based on the leaving condenser water set point instead of a chilled water temperature. In short, the same logic we've been discussing applies to the condenser side. A larger delta T is common for condenser when heating, so let's use a 30-degree delta T here. Each compressor still does half the delta T, so here each compressor does a 15-degree delta. It is important to note that the only time I am making the 120-degree set point is when we have 90 degrees entering and both compressors are on. All other points are achieved by cycling compressors on and off. In this example, if 95-degree water is entering the condenser, telling the chiller heater there is less than a full requirement for heat, only 1 compressor may be operating. If each compressor is doing a 15-degree delta T, this means that the hot water output on the condenser would be 110 degrees off, and we would be 10 degrees off of the hot water set point. What I want you to internalize here is that the situation is the same as what we looked at on the chilled water side, but because the delta T is larger, the variance from the set point is larger.
Esti, this all makes sense. We talked about how part load operation impacts the leaving chilled water temperature, delta T, number of modules, but can we put this together into a general summary?
Good idea, Sarah. We really can summarize temperature control as a function of delta T and quantity of compressors in a table like this. As the number of compressors increase, each makes up a smaller percentage of the overall chiller output. As delta T decreases, temperature control also improves. With a 10-degree delta T and only 2 compressors, each compressor is responsible for 5 degrees, meaning one could expect temperature swings of 5 degrees when a compressor stages on and off. If this was a controlled process or the specification required temperature control of plus or minus 1 degree, then a 5-module solution with 10 total compressors would be a better fit. There is another important component of temperature control that we haven't talked about yet: flow. The standard flow calculation equation you've seen before is shown at the top of the slide with the bottom format solving for GPM instead of tons. Tons multiplied by 24 divided by delta T equals GPM. We already showed how if only 1 compressor is running, you have half the tonnage and therefore half the delta T. Now let's focus on how flow affects our modular chiller performance. Remember, this equation applies to each module individually, as each module is a chiller in itself. This equation also means that anytime you vary flow to a module, you are changing the delta T. If you have a constant entering chilled water temperature and you decrease flow, your leaving chilled water temperature will drop. Let's look at an example. Here we are using a 50-ton module. When the module gets 75 GPM in chilled water flow, the delta T is 6044. However, If the flow were to decrease to 50 GPM, that widens the delta T. The entering temperature to the chiller remained the same, which means the leaving chilled water temperature has to decrease as a result. In this example, if flow decreased to 50 GPM, the module would try to make 36-degree water and likely would hit a low temperature alarm. If you have an existing modular system that has low temperature alarms, it very likely is related to a flow issue. The same issue can happen on the condenser side of the module, resulting in too high of leaving condenser water temperatures. Just remember, flow is very important to a modular chiller since you are really utilizing multiple chillers in parallel. Dan will be focusing on flow control with your modular chiller in the next section. Now, if you were watching these last couple of slides and were thinking the temperature swings with on-off scroll compressors were too large, then using a compressor technology with capacity control might be the right solution for you. Variable speed drives can be applied to scroll compressors to achieve tighter temperature and capacity control, as well as the added benefit of better part load efficiency for your design. Modular designs often have flexibility in how many variable speed compressors to utilize in your design. 1 or 2 variable speed compressors make a large impact on a single module, but adding more variable speed compressors has a diminishing returns in a large chiller bank. As shown on this slide, centrifugal compressor designed with an integral drive could be a great choice. Same benefits of modular, very efficient, oil-free, and offered with shell and tube heat exchangers. Digital scrolls or screw compressors could be an option from some manufacturers as well. The important takeaway here is you should evaluate how much temperature fluctuation is acceptable upfront in your system design. Comfort cooling applications may not have an issue. However, if you do need tighter temperature control, smaller design delta Ts, compressors with capacity control, or adding more modules are all strategies to consider. Another option could be to address temperature control not with the modular chiller itself, but with your system design. For example, your modular chiller temperature output could vary, but you could be utilizing a 3-way thermostatically controlled mixing valve in the system for control instead. Pulling off a mixing tank in the system is also a common design used to provide a blended water supply. Overall, we always need to make sure that we select the steps of control, delta T, and system design that is compatible with your system. The last topic I'm going to touch briefly upon today is installation. Part of planning for your successful modular chiller design is making sure your customer is educated and prepared for a modular chiller installation. Shown on the slide is sample piping schematic where I want to highlight both a couple of chiller and field assembly notes. The first point I'll make is that a modular chiller requires some field assembly to connect the modules to each other. This point seems straightforward, but is worth noting as making the groove coupling connections between modules can be a fair amount of work. Assembly involves sliding the modules together, making sure they're at equal elevations, and lining up the headers. For a water-cooled chiller with 5 modules, this means you have 16 grooved couplings to connect internally to the chiller. Another item that will need to be field installed is control wiring. The controllers of each module will need to be connected with control wiring. You will also note there are temperature sensors shown external to the chiller. Each module monitors temperature on its own internally, but as your modular chiller is several chillers in parallel, you also need to get a good reading on the mixed water temperature output of the chiller bank. These external system temperature sensors ship loose and will be field wired back to the primary controller. Lastly, under the field installed items, I have listed a differential pressure transducer. This may or may not be used depending on how your chiller is operating in a variable flow system. Dan will talk more about this in a minute. Under the installed on modules items, we have listed motorized valves, flow switches, and strainers. Flow switches and strainers could be installed on the modular level or the system level, depending on the manufacturer, so take note of these items prior to install. Hopefully this brought some awareness to some of the nuances of installing modular chillers, but of course, please refer to your specific installation manual for details. My final thoughts on equipment considerations are simply to focus on the upfront planning of your modular chiller. Now that you understand how compressor staging works between different modules, you can use this as a tool for determining how many and what type of modules should be used in your chiller plant design. Sometimes this may also mean incorporating hydronic components such as valves and tanks in the chiller plant for overall effectiveness. Make sure all the needed hydronic and control components are in place so installation into your system goes smoothly. And now, speaking of system control, I will turn it over to Dan Gentry to discuss system considerations and variable flow pumping with modular chillers.
Great information, Esti. Now that we understand equipment considerations specific to modular chillers, we can now explore some system considerations. In this section, we will look at system pumping examples, chiller features related to pumping strategies, variable primary flow pumping, and system loop volume considerations. To set the stage, let's review a basic primary-secondary system consisting of two packaged chillers, piped in parallel. Each chiller has a dedicated pump. A decoupler pipe hydronically separates the primary and secondary loops. When more system flow is needed, another pump and chiller combination are energized. The chillers would then modulate their compressors to provide the desired leaving fluid temperature. Secondary pumps then maintain the desired system DP. This could also be configured to be a variable primary, variable secondary, and both systems are commonly seen today. So what does this look like with a modular chiller? Here we have a chiller consisting of 3 modules, similar to what Sarah introduced. The modules are piped in parallel with one another and are of the same size and pressure drop, so each module will see the same proportion of flow at all times. In this example, the primary pumps provide 300 GPM to the chiller, so each module will see 100 GPM. In contrast to the previous system, where a chiller seeing flow would typically be operating, the chiller, or all 3 modules, see a constant design flow rate and stage compressors on and off to maintain the desired leaving fluid temperature. The temperature of the fluid leaving the chiller will be dependent upon the return water temperature and quantity of compressors in operation, as Esti described earlier. When the chiller is below fully loaded, the leaving temperature is a mixture of conditioned and unconditioned fluid. Today, we often see variable flow systems preferred by designers over constant flow for modular chillers in an effort to avoid mixing of unconditioned fluid. The following example is meant to help illustrate how a modular chiller functions in a constant volume pumping system and why variable flow might be considered. All right, let's put some numbers to the system and walk through some operation. The chilled water design conditions are 60-degree return with 44-degree supply at 300 GPM. The present system load is about 135 tons and is satisfied with 200 GPM of approximately 43-degree chilled water. The coils return a 16-degree delta T. Because the system only needs 200 GPM, this means that 100 GPM is going through the decoupler. When 200 GPM of 59-degree chilled water mixed with 100 GPM of 43-degree chilled water, the return temperature to the chiller is 54 degrees. Because the return temperature is lower than design, this would indicate to the chiller controller that less than full load will satisfy the system demand. In this example, 2 of 3 modules are operating. Because each module is designed to produce a 16-degree delta T when given 100 GPM, the 2 modules in operation will make 38-degree fluid leaving their heat exchangers, while the off module will do no work. The resulting mixed fluid temperature leaving the chiller will be 43.3 degrees. The key design consideration here is that you can expect to see varying leaving fluid temperatures at part load conditions. This example works well, but are we missing something? What if one module is operating? Working through our example again, but with 67 tons of load instead of 135, we can reevaluate what the chiller would see. Now we see a mixed return temperature to the chiller of 48.6 degrees. With only one module now required to meet the load, this increases the amount of mixing within the modules. Now 100 GPM of 32.6 degree chilled water mixes with 200 GPM of 48.6 degree chilled water for a leaving chilled water temperature of 43.3 degrees. This may look okay, but we have to consider that the chiller controls must also protect itself from freezing. To do this, the controls limit the module level leaving water temperature to 36 degrees. So in this example, the module in operation would actually shut itself off to protect the heat exchanger from freezing. After all timers have been satisfied, the next available compressor would be energized. This condition could lead to excessive compressor cycling and varying temperature swings. A variable speed compressor on the first stage could be an option to consider here. This example highlights the importance of design delta T, desired leaving fluid temperature, and quantity of modules, and the effect they have on system operation. This is a major reason designers will more likely consider variable primary flow in modular chiller systems consisting of more than 3 modules. This is not to say constant volume pumping cannot be done, but care must be taken when designing and selecting the system. So what can be done to address this problematic situation? Well, there are a few practical ways this can be addressed. The first one is using a glycol mixture instead of pure water. Using glycol in a chiller not only protects the heat exchanger from freezing, but it also means the tripping point of the freeze protection can be lowered to a point that aligns with the freeze protection level of the glycol used. Consider the chilled water temperature for the application. The warmer the chilled water design temperature is, means the further the controls are from the low temperature tripping point. Also consider that modular chiller manufacturers may recommend or require glycol in the evaporator loop when leaving fluid temperatures may be below 42 degrees. The intent here is again to protect the braze plate heat exchanger from freezing. A variable speed compressor can help with turn down, temperature control, and reduced cycling. This could be applied to 1 or more compressors. The last item to consider is variable primary flow. When a modular chiller is configured in a variable flow system, the modules that are in operation would see flow, while the off modules see no flow. This eliminates mixing of conditioned and returned fluid within the chiller. We will explore variable primary flow in the coming section. I mentioned automatic isolation valves earlier, and now we will see what this feature can offer when configured in a modular chiller. One of the primary system drivers for automatic isolation valves is variable primary flow. When a unit will be installed in a system that varies the rate of flow through the chiller, these valves are a requirement in the modular chiller for proper operation. The control logic for these valves is such that when at least one compressor is energized in a module, the motorized isolation valve in that module will be open. When both compressors are off, the valves are closed. Consider a comparison between multiple chillers piped in parallel in a modular chiller. In the package chiller plant, each chiller will have its own isolation valve. In the modular chiller, these valves are installed in each module. Each heat exchanger in the array would include a motorized isolation valve. This is applicable to the evaporator and condenser sides independently. The valves are placed within the module and are located between the heat exchanger and header system and are installed and wired at the factory. In addition to allowing for variable flow operation, automatic isolation valves offer additional system features. When water-cooled chillers are operated year-round, there likely will be times when the entering condenser water gets quite cold. In these instances, package chillers require an external system to maintain a minimum entering condenser water temperature. Common means to achieve this could be a throttling valve, as shown here, cooling tower bypass, chiller bypass, or condenser pump speed control. So what about modular chillers? When a modular chiller is configured with the motorized isolation valves on the condenser side, they are capable of modulating to maintain the required leaving condenser fluid temperature to maintain refrigerant head pressure control. Once the entering fluid drops below a given temperature, for example 55, the valve will begin to pinch down, reducing the flow rate through the condenser and in turn raising the temperature of the leaving fluid to an appropriate level. This eliminates the need for field-installed and controlled devices and simplifies the design, install, and operation of the chiller plant. Note that when using this method of head pressure control, that pump speed should be controlled via differential pressure instead of a flow meter, as a flow meter and the chiller valves tend to fight one another. We discussed how motorized valves are required in variable flow systems, and that when compressors are off, the valves will be closed. So what happens if our chiller is off and all the valves are closed, and the pump is still on? Where does the flow go? In this scenario, it couldn't go anywhere, and the chiller would cause the pump to deadhead. In this case, we have two options to consider. The first option is installing a bypass line and valve external to the chiller, sized for the minimum flow of the system. The second option to consider is to elect to keep one valve open at all times to act as the chiller minimum flow bypass, eliminating the need for external means. Note that in some applications, an external bypass may still be required based on minimum flow requirements. Now we understand that the modules within a modular chiller are piped in parallel, so each module sees the same portion of flow. So what happens when these motorized isolation valves open or close? Let's take a look. Here is our 3-module example with a design flow rate of 300 GPM. Here the chiller is running at full load, but the system is starting to become satisfied, so the chiller can begin to shut off compressors and close isolation valves. With the system load being reduced, the chiller can unload or stage off compressors. Now only 2 modules are operating, so the valve in the 3rd module is closed. With the system pump still moving 300 GPM through the chiller, but only 2 valves open, the operating modules now see 150 GPM. Or 50% above design flow rate. Because the modules are designed to provide a specific delta T at a given flow rate, we want to see that design flow rate maintained, which leads us outside of the chiller and over to the pumps. How do we control pumps in order to maintain the desired flow rate for the chiller? Before we get into our modular chiller flow control, let's look at a system with package chillers. Again, we will reference a common variable primary flow system consisting of multiple package chillers to set up a comparison to a modular chiller plant. As we walk around the system, we see the defining features of a traditional variable primary flow system: manifolded pumps with VFDs, automatic chiller isolation valves, minimum flow bypass with modulating valve, and two-way valves at the terminal devices. So what does this look like when we replace the package chillers with a modular chiller? First, we must recognize the system components that are required for proper operation. As with any variable flow system, variable speed drives are supplied with the system pumps. This should be straightforward, as VFDs are the most common way to modulate flow in a system. The chiller must be configured with motorized automatic isolation valves per module. These valves are the key feature built into the chiller that allow for proper variable primary flow operation. Limit three-way valves in favor of two-way valves to minimize minimum flow. This item is key to maximizing pump savings. A benefit to using modular chillers is they can often be selected to achieve very low flow turndown. By matching the amount of bypass in the system to the minimum flow of the chiller, the maximum pump energy savings can be realized. A modulating end-of-loop bypass or quantity of three-way valves appropriately sized for the application, more to come on this. System differential pressure and chiller differential pressure or a flow meter for the chiller are required. Because there are both modulating valves in the system and in the chiller, we need to see a DP or flow rate for both. The control of these can change once they are in place, but it is key that both are installed in the system. Oftentimes, a flow meter is preferred for the chiller as it can provide better accuracy, especially when the chiller DP is relatively low. And last, as with any chilled water system, a minimum loop volume is required for stable system operation. These would be considered the minimum system requirements. As long as these basic components are provided, variable primary flow can be accomplished in several ways. We have talked about bypasses a bit, and now we need to clarify one more: the end-of-loop bypass. As previously mentioned, it is this bypass, located out in the system, that allows for enough flow to be returned to the chiller when the system valves are closing, so minimum flow is always respected. The location of this bypass should be as close to the end of the loop as possible, or at least 2 minutes of volume. This allows for enough loop time for the chiller to be able to safely unload. A bypass located in the plant room or too close to the chiller will result in a short loop time when the bypass is open, directing chilled water back to the chiller and leading to potential nuisance trips as the chiller needs time to unload. The control of this valve needs to be fast-acting. It is recommended to use a direct controller for this valve instead of running the control through a BAS. This will allow for a quicker response time for the valve to open and close when needed. Last, the valve should be sized appropriately for the application. Typically, this value is around 1.5 times the design flow rate of a single module for common comfort cooling applications, though chilled water temperatures and glycol may influence this number. A critical cooling application typically would use a larger bypass.
But what about loop volume? I heard you all asking this through my monitor. And of course, this is a great question. 2 or 3 minutes are the typical rules of thumb used by our industry on the chilled water side. The good news is, it still applies to modular chillers applied for comfort cooling. The easy way to calculate is to multiply chiller design flow by 3. This gives you the required system volume if you're shooting for 3 minutes. Even when there's a bypass valve out in the system, adequate loop time is still required. If the bypass is too close to the chiller, it may not have enough time to stage off compressors. Add a buffer tank to add loop volume when the evaporator, system piping, and coils are inadequate. Of course, some applications may require longer loop times. A process load with tight temperature requirements or an air-to-water heat pump design that incorporates defrost mode are typical applications in which more loop volume should be considered. Please reference the specific requirements of your application. So, Dan, let's talk about minimum flows with these chillers.
Thanks, Sarah. We have mentioned minimum flow, but how is this determined for a modular chiller? First, we have to separate module and modular chiller. The minimum flow of a modular chiller configured with motorized isolation valves is simply the design flow rate of one module. For example, let's look at a 4-module chiller. The design flow rate of the chiller is 400 GPM, meaning that each module sees 100 GPM. Therefore, the minimum flow of the chiller is 100 GPM. Minimum flow for a module isn't as straightforward. When looking at a single module, we have to consider the design conditions. An 8-degree delta T would yield a higher flow rate compared to an 18-degree delta T, and the same module could be used in either case. Because the chiller and system are designed for a specific delta T, which corresponds to a flow rate, it is then this flow rate that is the minimum flow for the module to maintain the design delta T. All right, now let's put the components we defined into our system with a modular chiller. Here we see a single modular chiller in a variable primary flow system that appears a little different from our previous system. Let's walk through this system and find out what is the same and what is different and why. First, which is the same as the previous system, we have pumps fitted with VFDs. There are multiple ways these pumps can be controlled, and we will explore some of those strategies towards the end of this section. Second is that the modular chiller is configured with automatic isolation valves. The third item is minimizing 3-way valves in favor of 2-way valves. The intent of this is to maximize flow turn down and thus realize pump energy savings. When too many 3-way valves are used, this leads to more mixing of unconditioned fluid and can lead to system issues like low delta T. The fourth item is an end-of-loop modulating bypass, which was previously discussed. An item we don't see shown is a chiller minimum flow bypass, and for good reason, because it can be internal to the chiller, as previously discussed. There will also need to be a controller installed that coordinates these components. There are several ways to control variable speed pumps with modular chillers in a variable flow environment, and we will not be able to cover all of them here, but we will review some options. As long as the main system components that were previously covered are in place, the system can be controlled in multiple possible ways. Okay, let's walk through how this could be accomplished. In this setup, The pump speed is primarily driven by an output from the chiller controller to a system controller signaling how many modules are operating. The flow rate of the chiller is also sent to the system controller, which can increase the pump speed if required. A situation that could cause the flow meter to increase the pump speed could be if the module strainers are plugged and nominal flow is reduced. As more modules stage on, the system controller will increase the pump speed accordingly in a stepped fashion, providing constant design flow per module. This results in a system delivering a fixed delta T. Because the system is designed to deliver a constant delta T, there should be less mixing within the modules so better temperature control can be achieved. How about unloading? As the system starts to become satisfied, the two-way valves start to modulate closed. The system differential pressure begins to rise. As this happens, the end-of-loop bypass valve modulates open to maintain the desired system pressure. As the return temperature to the chiller lowers, the chiller controller will begin to stage modules off, closing their automatic isolation valves, in turn signaling the system controller to lower the pump speed. In this example, the pumps always keep the chiller satisfied, and the end-of-loop bypass maintains system pressure and ensures minimum flow to the chiller. Another potential control strategy could utilize differential pressure instead of an output from the chiller controller and a flow meter. In this configuration, a chiller differential pressure is maintained by the pump. The pumps are controlled to a constant chiller differential pressure. As the automatic isolation valves modulate open and close, the pumps track up and down, maintaining design flow to the number of operating modules. As an alternate control strategy, the pumps could also be controlled to maintain a system pressure. Either control method should be fast-acting and not go through a BAS that could slow down the control response. In either system, it is recommended to use a high-quality components with high accuracy capabilities. The system side would operate in the same fashion as the previous example. We have focused on chilled water so far, but what about the condenser side? Can variable flow be applied here too? The answer is yes, it can. While not as common on the heat rejection or cooling tower side, varying the flow rate can be done and is a bit more simplified. Because there are no valves or loads shutting down on the cooling tower side, we can simply control the pumps to maintain the desired flow at the condenser. How about heat recovery? Yes, that can be done as well, and the same rules for the chilled water side can be applied to the heating water side.
We have only covered a few pumping arrangements for modular chillers in this section. For more information and more examples on pumping system control, please see our application guide pertaining to modular chillers and VPF systems, which is also referenced in the bibliography of this program. Next, Sarah is going to cover some common applications for modular chillers.
So, when would a modular chiller be a better fit than a package chiller? And how is compliance with standards and codes impacted? Let's assume this represents the building footprint of an upstart brewery. When the facility expands, shown in yellow, a modular chiller lends itself to incremental capacity increases. Adding another module to the existing chiller, especially with forethought during plant design, can be simpler than adding a packaged chiller. The headers and plant piping should be sized for the maximum expected capacity up front. Structural supports and the base frame are installed early on as well, but the equipment costs can be delayed until the capacity becomes needed, especially if growth differs from forecast. Smaller units reduce redundant capacity. Take a 200-ton chiller plant with a pair of 100-ton package chillers. To achieve N+1 redundancy, a third 100-ton chiller is required. Using 5 40-ton modules instead, only a 6th 40-ton module is required to meet N+1. And these platforms are flexible. Modular heat pumps can be used for seasonal coverage or in changeover systems as chiller heaters. And heat recovery is an option as well. Instead of throwing that heat away that we just removed from the building, recapture it to temper fluid or air elsewhere in the building, perhaps reheat loads or service water preheat. 6-pipe modular units exchange heat with a third fluid as a source or sink. When the project location lends itself to a ground loop or is nearby a body of water, modular units can be implemented as ground source heat pumps to heat or cool using a more moderate source temperature than seasonally available, improving efficiency by moving BTUs around in either direction. Assuming adequate glycol, modular chillers can be applied in thermal energy storage systems to build ice. And speaking of heat recovery, let's apply that concept to a process load. A process may have a dedicated chiller, or multiple temperatures may be required for several processes. Heat energy may need to be added or removed. A given heating process load might be fairly constant throughout the year, so there may be a consistent sink for heat removed from a building. We can leverage that process to reuse heat removed elsewhere, or vice versa. Often, chiller plants have equal-sized chillers within the plant. However, by analyzing the number of hours spent at various load points, asymmetric design may be desirable. A pony chiller is often used at night or under low load conditions and is sized just right for those expected load conditions. It might be used as a peak chiller too, when a bit more capacity is needed than is available from the remaining plant chillers. A swing chiller is often sized at 1 to 2/3 that of the other chillers in the plant. It's sequenced on and off in between larger chillers to more closely match the plant capacity to the cooling loads, as chillers are added and subtracted with demand fluctuations. A building model early in design or historical data from a building automation system in a retrofit opportunity allows for judicious sizing of chillers in an asymmetric plant. An example might be a community center that has a 200-ton chiller installed. When the local Cub Scout troops and knitting clubs hold Monday night meetings, with the rest of the building essentially unoccupied, a single large chiller may not have enough turndown. A 30-ton modular pony chiller with 2 modules can meet this load without tripping and generating a service call. Retrofits are another application where modular chillers can make sense. Historical preservation may be desirable to maintain architectural elements and historic character. Let's consider a museum retrofit. The mechanical room is in the basement with limited access. A module fits in a standard passenger elevator and through a single door. Rather than disassembling a package chiller, the modules can be moved right in, simplifying installation. Another feature typically seen in packaged chillers is relevant to modular chillers. Air-cooled modular chillers are available with hydronic free cooling coils, aka a water-side economizer. The fluid is routed into coils nested with the condenser coils to be cooled rather than running the compressor when conditions are favorable. A free cooling only module can be included in a chiller bank, acting as a fluid cooler on its own. When connected as the first in the bank, integrated operation is doable too, cooling the fluid as far as it can. The remaining modules can pick up the rest of the load. Data centers, because they are conditioned to warmer space temperatures, are suitable applications for free cooling. And as the site expands, dedicated free cooling modules can be added provided piping, headers, and supports are initially sized for the maximum expected capacity.
What about standards? Do modular chillers impact compliance?
Great question, Dan. ASHRAE Standard 15, the safety standard for refrigeration systems, uses the charge in the largest independent refrigeration circuit when determining whether the system complies with the refrigeration concentration limit, or RCL. The RCL for a specific installation depends on the type of refrigerant and occupancy classification type. Because each circuit in a modular chiller tends to contain less charge than a conventional package chiller, the RCL is less likely to be exceeded for the same net capacity. A quick example, this 120-ton water-cooled rotary chiller contains 2 circuits, each containing 132 pounds of charge. The RCL is calculated based on 132 pounds for the given space volume. If instead 4 30-ton modules are used, each of the 8 circuits contains 16 pounds of charge. So the RCL is calculated based only on 16 pounds rather than the 132 pounds. This decreases the potential charge release for the same space volume by a single circuit. If this happens in the machinery room, mechanical ventilation must be activated to disperse the charge. With less refrigerant released, assuming the same type of refrigerant is in each chiller, less ventilation is required for dispersal. Therefore, fans and ductwork may be smaller for a modular chiller when compared against a packaged chiller of the same net capacity for the same sized machinery room. To learn more about ASHRAE Standard 15, refer to the 2021 Engineers Newsletter and Engineers Newsletter Live programs or the standard itself, all referenced in the bibliography for this program. And last but not least, a nod to ASHRAE Standard 90.1. It's common for our product support and modeling engineers to receive questions about the efficiency requirements within the tables of Section 6.8. Just as for traditional packaged chillers, either Path A or Path B can be chosen for compliance. Whichever path is chosen, both the full and part load efficiency requirements must be met. Assuming a chiller uses scroll compressors, the equipment type is positive displacement. Here's where things are a little different from what we're used to. In a standard chiller plant using packaged equipment, the chiller capacity row is based on the individual chiller. For a modular chiller, because each module is itself a chiller, the capacity is based on the module size. Each module is certified as a single chiller. The chiller itself doesn't receive a rating, rather each module does. As an example, if a 500-ton modular water-cooled scroll chiller consists of 10 50-ton modules, the efficiency requirements come from the less than 75 tons row in the table. So to summarize, modular chiller systems allow for flexibility in design. Water or air-cooled units are available with heat recovery or free cooling options. And modular chillers are available as heat pumps for applications requiring heating in support of electrification initiatives. 2, 4, and 6 pipe units can be applied to meet specific design requirements. Modular chiller capacity can be increased later on by adding more modules, simplifying planned expansion. Redundant capacity can be reduced because of modular chillers' smaller nature, and service follows suit because a module can be isolated from the system while the remaining units continue to condition system fluid. And in retrofit jobs where minimal construction is desired or accessibility is tight, their small size can make installation faster and less intrusive to building occupants, all while keeping compliance with standards in mind.
Let's recap the key takeaways from today's program. Every module is a chiller itself, so a modular design is actually several chillers in parallel. The modular chiller provides a single point of water connection to the chilled water system, as well as a single point of control to the BAS, so it looks and acts like a single chiller from the outside. But certain design considerations must be reviewed when looking at the parallel flow arrangement and the mixed water output of a modular chiller. The appropriate type and number of modules must be used to design your modular chiller plant. This is important to get the right level of redundancy and temperature control for your application. On-off scroll compressor installations with few modules and wide delta T's can lead to large swings in supply temperatures or even nuisance alarms. Additional steps of control or variable speed compressors are often employed as ways to provide more stable temperature control. Next, we looked at how modular chillers act differently in constant primary flow and variable primary flow systems due to having modules in a parallel flow arrangement. We learned that when modular chillers are applied in constant flow systems, each module within the chiller sees its design flow all of the time, even when its compressors aren't running. Individual refrigerant circuits are staged on and off to maintain leaving chilled water temperature as a system demand fluctuates, resulting in a mixed water temperature at the chiller output. For this reason, variable primary flow is more commonly applied today and the preferred configuration for temperature control with modular chillers. Modular chillers installed in variable flow applications must use motorized valves that open when a module has compressors operating and close as the module is staged down to prevent any bypassed flow through an off module. As we stage on more modules and valves open, more paths for water flow are created, resulting in a decreased differential pressure across the modular chiller. Flow to the modular chiller must then increase to maintain design conditions. Terminal devices with two-way valves and a system bypass valve complete the installation. Flow control can be achieved in multiple ways. Controlling either the pump or system bypass to differential pressure is a common strategy. Flow could also be addressed with control logic that looks at how many modules are operating and adjusts flow accordingly. The important point is not which flow strategy is used, but that flow is indeed part of the upfront control design. Using the design and control strategies discussed today will make for a successful modular installation and allow you to take advantage of the benefits of modular chillers. I'll now turn it back over to Jeanne for wrap-up.
So that's our overview of modular chiller systems. We hope you found today's program a helpful way to learn about this subject. As always, the bibliography included in your handout provides more information on where to find a number of resources related to today's topic. Or contact your local Trane account manager for specific information on Trane systems, equipment, controls, and services. For those of you seeking continuing education credit, check out the newest online courses offered on Trane Education Center, free and on demand. And please don't forget to fill out a survey to let us know what you thought of today's program. AIA members, please turn in your member information to your local Trane office, or if watching online, submit your information to enl@trane.com. And finally, for those of you viewing in person, please ask your local host about details for the remaining Engineers Newsletter Live programs, or check out trane.com/enl. Thanks for joining us today. We look forward to seeing you next time.